Thank you all for attending our first Paul G. Allen Distinguished Lecture of 2026. Today it's my pleasure to introduce Professor Scott Aaronson at the University of Texas at Austin, where he is the Schlumberger Chair of CS and the founding director of its Quantum Information Center. Scott got his bachelor's from Cornell University, PhD from UC Berkeley, and he's a theoretical computer scientist whose research has focused on the capabilities and limits of quantum computation. In addition, he's a prolific writer, known both for his book, Quantum Computing Since Democritus, and his very well-known blog, Shtetl Optimized. He received the NSF Foundation's Alan T. Waterman Award, the US PCAS Award, the Tomasori Chiesi Prize in Physics, the 2020 ACM Prize in Computing, and is both a fellow of the ACM and the AAS. In my opinion, Scott, among all theoretical computer scientists, has a real penchant for seeing physics through a distinctly computational lens and for making seemingly intimidating physics more tractable. So please join me in welcoming Scott Aaronson today.
All right. Well, thank you so much, Chinmay. It is wonderful to be back here at UW, where I have so many wonderful friends and colleagues from over such a long time, now including Chinmay also. But, you know, I was just at SeaTac Airport last night thinking, wait, you know, how does the Uber lot work here again? And then I remembered that last time I was here, Uber didn't exist yet. Okay, so it's been too long, but it's great to be back. This is a little bit of a spouty talk. This talk was originally designed for a philosophy department. I gave it at Columbia, but then Chinmay said that he would be interested in my giving it here. So hopefully, if you like CS or you like physics or philosophy or any non-empty subset, then this talk will have something for you. Yeah, it's called Computational Complexity and Explanations in Physics. So, you know, what is computational complexity? I mean, this is a CS department, so, you know, probably you've, you know, at least seen it before, but I would call it the study of the inherent resources, like time and memory, also other things like randomness, quantumness, that are needed to solve computational problems, and especially how those resources scale with the size of the problem that we're trying to solve. Like, do they scale polynomially? Do they scale exponentially? You know, we can ask more fine-grained questions than that. We can try to shave off log factors if we really care. Okay, but mostly, you know, we are interested in sort of the broad scaling behavior. So sort of the features of the, you know, hardness or easiness of a problem that don't depend that much on the details of what programming language or what chip architecture are we using, but that just depend broadly on what kind of computer do we have, or like what kinds of laws of physics, you know, does it operate according to. Now, you know, there are many different reasons why problems might be hard to solve, right, or impossible to solve. You know, those include, you know, that we have limited information, you know, the garbage in, garbage out problem, right? We just do not have all the relevant data. Okay, or related to that is chaos, okay, that, you know, many physical systems might be hard to predict because we just cannot measure, you know, the initial state to requisite precision, you know, and any small error is going to blow up exponentially over time, you know, even if, you know, and that would still be true even if we had an infinitely fast computer. Okay, and then, you know, there's all sorts of, you know, irrationality, as, you know, we are reminded every time we read the news these days. Okay, that may prevent us from, you know, making the right decision, even if we have all the information and all the computing power. Okay, but, you know, here we're specifically interested in computational intractability. Okay, which is like reasons why a problem could be hard to solve that are purely because of sort of not having the right computational resources, okay? That, we have all the data that we need. If we had an infinitely fast computer, then we could process that data and learn what we want, but we don't, okay? We don't have that computer. So, I mean, people have been, aware of this for a very long time. I mean, even Euclid in 300 BC was talking about, how to speed up computations. For example, for computing the greatest common divisor between two integers. Although, we only systematized, the theory of what is computable at all in the 1930s. And then we started systematizing the theory of what can be efficiently computed, around the 1960s. Okay, so there's a quote that I really love. Yeah. Sure, whatever.
On the last one with chaos, is that really not a complexity subject?
I think I would argue that it isn't, because here the point is that even if you had an infinitely fast computer, right? There may be a limit to how far in the future you can predict the weather, for example, right? And that limit is not coming from computational intractability. It's coming from the fact that you cannot measure the state of all the atoms in the atmosphere to a requisite precision.
I see.
Yeah. Okay. Good. So, so the quote from Alan T. Okay, he says, this is from his famous paper on, the imitation game. Okay, he says, the view that machines cannot give rise to surprises is due, I believe, to a fallacy to which mathematicians and philosophers are particularly subject. This is the assumption that as soon as a fact is presented to a mind, all consequences of that fact spring into the mind simultaneously with it. It is a very useful assumption under many circumstances, but one too easily forgets that it is false. Okay? So, the basic question, and this is something that I've wondered about for a while. I actually wrote a whole survey article back in 2011, which was called "Why Philosophers Should Care About Computational Complexity." Okay, and actually, amusingly, if you type into Google "why philosophers should," it fills it in with "care about computational complexity." Okay, so. But should they care, right? Or if you just care about it would be very easy to take the position that certainly even if you care whether something is computable or not, once you know it's computable, how many steps does it take to compute it? This is some nitty-gritty quantitative question, right? This is really not of broader philosophical interest, or not of let's say it seems like certainly it's a question that matters technologically. In this talk, I want to ask specifically, does it matter for explanations in physics? Okay, and what do I mean by that? So it is clear that computational hardness or easiness of problems could matter a lot for our ability to know the laws of physics. Okay, here is a picture of one of the computing clusters that they use to analyze data from the Large Hadron Collider in Geneva, right? And I've actually gone to visit the CMS detector that they have there. It's one of the wonders of the world. Okay, but before you see the detector, you just see rows and rows of computers. Okay, that are used to analyze all the particle collision events, decide which ones to save for later processing. Okay, so they're clearly involves a massive amount of computing power, and you could even wonder, are there interesting new physical events that are being missed just because of a lack of enough computing power to analyze all the data that's coming out of that? Okay, so so clearly, if you cared about such things, you would care about how much computation do you have, right? Right now, like half of the world's economy is being diverted to just construct bigger and more and more data centers, right, to run a lot of it to run AI with. Okay, and so certainly it is natural to realize that, okay, certainly if AI is going to play more and more of a role in like doing science for us or doing physics, then how much computing power do we have will be a key question. Okay, but in this talk I want to focus on a different question, which is, can computational complexity play a direct role in our explanations of the laws of physics themselves? Okay, so when we're explaining, like, why are the laws of physics like this and not like that? Okay, is computational difficulty relevant for that? Okay, and you might worry, it's just too anthropocentric, right? It's a thing that humans care about because humans want to compute stuff, but it just doesn't seem like a thing that the laws of physics ought to care about. Okay, that's a position that you could take. Rather than just debating this in the abstract, what I want to do in this talk is basically just talk about 3 different case studies. Okay, where some people have argued that sort of computational complexity is sort of directly relevant to explaining something about fundamental physics. Okay, and we'll try to explore those. Okay, the first one is about quantum computing and the many worlds interpretation of quantum mechanics. Okay, and this is sort of an old debate that goes back decades, I would say. But I will tie in some what is happening recently in quantum computing here. The second is what I'll call actually what I like to call Occam's razor with complexity theoretic aftershave. Okay, so should we value, when searching for explanations, in physics, for example, should we value not only the simplest explanation, but the simplest explanation that is computationally efficient? Okay, or whose predictions can be calculated in some reasonable amount of time? Like, is that a thing that we should value? How should we think about that? And then the third thing is sort of a more recent direction that really grew out of work in 2012 by Daniel Harlow and Patrick Hayden. Okay, about the black hole information paradox. But this is the use of computational complexity as what I'll call an armor for effective theories. That is, like, when we look at our effective theories in physics, like quantum field theory, general relativity, things that, like, we don't expect to be sort of the ultimate truth about nature, right? They're ultimately superseded by something else, but they have some regime of validity, right? Is computational complexity relevant to sort of delineating what that regime of validity is? Okay, and so they gave a very, very striking example, at least in the context of black holes, it seems like we need computational hardness to even say what is the regime of validity of our known laws of physics. I'll give a different speculative example that came out of some recent work that I did involving the second law of thermodynamics, or basically, like, if P equals NP, would we be able to violate the second law, build a Maxwell's demon, build a perpetual motion machine? Okay, I think that's a natural thing you could ask. People have kicked that idea around for decades, and so I'll give you sort of at least some insight about that, hopefully. Okay, so let's start with quantum computing and the many worlds interpretation. Okay, we're here, the question is, like, to explain how quantum computers get such huge speedups, are we forced to posit the reality of multiple universes, whatever we mean by that? Okay, so the first thing that I should do before, talking about such a heady question is to just back up a little bit and say, well, what is quantum computing? Because, this is, I think people are here from many different backgrounds. And to answer that, like I'm, because of my blog, for better or worse, like I'm, every couple days on the phone with another journalist saying, like, just explain in one sentence what a quantum computer is. Okay, and I'm like, I've been doing this for 20 years. And I'm like, can I have 10 minutes? Okay, because that's as far as I've managed to compress it. Okay, but the truth is that to answer the question, we have to back up a little bit and say, well, what is quantum mechanics, right? And quantum mechanics has been with us for literally a century now. Okay, but it's still, like, I think one of the worst popularized or most misexplained things in all of science. And the way that I try to teach quantum mechanics, and that many of my colleagues do in quantum computing and quantum information, is to teach it as something that's actually much simpler once you take the physics out of it. I like to teach it as a certain generalization of the rules of probability themselves. Okay, so a type of probability theory that now involves minus signs. Okay, so the famous two-slit experiment that Richard Feynman used to say, all of quantum mechanics is contained in this one experiment. Okay, so it just involves, let's say, a photon. That's what a photon looks like, by the way, or might as well for my purpose. Okay, and now we shoot it, over and over again at a screen that's got, that has two different holes in it that we can open. Okay, and we look at what is the probability that this photon lands at a certain spot that's on a second screen behind the first one, okay? And let's say that if this hole is open, then the photon lands at this spot with some probability, which is P1, okay? And the details of why I don't really care about, okay? Like it can go through this hole, and then it can, goes off in various directions, but sometimes it lands here, okay? Now there's a second hole, and if that hole is open, then the photon lands at this same spot with a probability equal to P2. Right? And now we open both holes, okay? And now, someone like me would be tempted to say it is just an a priori mathematical fact, right? It is something we don't need to even consult the physicists about, that we just know, sitting in our armchairs, that the probability that the photon lands at this spot is now P1 plus P2, right? Because we just add up from the two different ways it can go. Okay? The only problem is you do the experiment, and that's not the case. Okay? So what do you find instead? Well, you find, this thing that like drove people up a wall between 1900 and 1925, and there's a long story about it, until finally they said, well, here's what's going on. Okay? What's going on is that you have to each path that the photon could take, you have to attach a complex number. Okay? You have to attach a number called an amplitude. Okay? So these amplitudes are very related to probabilities, but they're not probabilities, as we can see by the fact that they are complex numbers. Okay? And now the total amplitude that the photon lands at the spot is indeed equal to the sum of the amplitudes of all the individual paths that it could have taken to get there. Okay? So that part is just like probability theory. Then the probability that I see the photon when I look is equal to the square of the absolute value of the amplitude. Okay? So the result of this is that, for example, it might happen that the photon could take one path with an amplitude of 1/2 and the other path with an amplitude of -1/2. Okay? Now, if that happens, then the total amplitude, alpha, will actually be 0. Okay? Which means that the probability that I see the photon at that spot will also be 0. Okay? So it's like the two ways that the event could have happened have interfered destructively and have canceled each other out. Okay? And yet, you may notice that if I were to close one of the two holes, then now I have an amplitude that is only 1/2 or only -1/2, which means that now the probability is equal to this absolute square of that, which is 1/4, which means that now the photon can get there. Okay, so by decreasing the number of paths that the photon can take, I can increase the chance that it gets there. Okay, and that's the sort of signature that we're not just dealing with some fiddly detail of particle behavior. We're dealing with a change to the rules of probability themselves. Yes?
So you used to say, and I really liked it, that quantum mechanics is probability theory with complex numbers.
Yeah, I
Which is more enlightening than saying with minus signs. Is there a reason it changed?
Well, I mean, you can say either. I think either version is fine, right? But most of the interesting things in quantum computing and information, we even see with just amplitudes that are positive and negative reals, right? The thing that we really, really need is just the fact that amplitudes can interfere and cancel each other out. Okay, the fact that they can also be complex numbers, does add a few important details. But for a lot of what we care about, just the fact that they have signs is enough. So we were having a conversation earlier this day where we were the subject of God came up, right? And I said the thing that I'm most confident about regarding God is that God really, really prefers complex numbers to real numbers, and the 2 norm to the 1 norm. So and then they urged me to say that in this talk, so I'm saying it now. All right. So, okay, so what is quantum computing? Well, here, I have the basic building block of a quantum computer is called a qubit. Qubit is just a bit that's got an amplitude to be 0 and another amplitude to be 1. So as we say, it can be in a superposition of the 0 state and the 1 state, okay, which we write like alpha 0 plus beta 1, and we use these ket signs, which are really just a notation for vectors. Okay, like these x's, these are a bunch of orthogonal basis vectors in a 2 to the n dimensional space. And now I'm just taking a linear combination of my basis vectors. So the key point is that to describe a qubit, I need 2 amplitudes. I need an amplitude for it being 0, an amplitude for it being 1. It is in a superposition of the 2 until I make a measurement, at which point nature has to probabilistically choose one or the other according to this rule here, which is called the Born rule. Okay. But now if I have 2 qubits, now I need 4 amplitudes. Right? I need an amplitude for 0, 0, for 0, 1, for 1, 0, and for 1, 1. If I have 3 qubits, I need 8 amplitudes. 4, I need 16, and so on. If I had 1,000 qubits, I need 2 to the 1,000 amplitudes, okay, which is more than could be written down in the observable universe. And yet, in some sense, our best theory of physics for 100 years tells us that they are all there, and for some definition of there. Okay, which of course we will want to come back to. Okay, and so the starting idea of quantum computing, which Richard Feynman and David Deutsch and a few other physicists started talking about 45 years ago, was if you really need a vector of 2 to the n complex numbers, to keep track of what n particles are doing. Let's say each particle might encode 1 qubit. So 1,000 particles, I could easily need 2 to the 1,000 amplitudes to describe them. Okay, then this seems like a staggering amount of computational effort for nature to be going to. It seems like, just to keep track of these 1,000 particles, nature has to maintain some scratch paper of size 2 to the 1,000. And every time something happens to the particles, nature has to cross off all the numbers on that scratch paper and replace them with new numbers. Okay, and actually the chemists and physicists have known that for generations. They've known it mostly as a practical problem, right? That if you're trying to use a classical computer to simulate quantum systems, then you may very quickly run into a limit of, the size of the quantum state that you can store or manipulate. But so then it was somewhat natural to ask, well, if nature is handing us this lemon, could we make lemonade out of it? right? Could we build a computer that itself would involve these gigantic superpositions? If so, what would it be good for? Okay? Now, Feynman and Deutsch, could only really suggest one good answer to that question, which is, well, it would be good for simulating quantum mechanics itself. Okay? We've been trying for decades to improve upon that answer with a few successes, but it is really crucial to understand, okay? Because unfortunately, almost any popular article that you will read about this subject will want to say, well, look, a classical computer just uses bits that are either 0 or 1, but a quantum computer uses qubits that can be 0 and 1 at the same time. So, if I have 100 qubits, that means I explore 2 to the 100 answers in parallel, and of course that's useful. That just solves, that just speeds up everything. Okay, unfortunately, it's not that simple. I've been, this is like a boulder that I've been pushing up a hill for 20 years. No matter how many journalists I explain it to, like they'll still, write the story the way they want. Okay, but since you're here listening to me, I'll tell you the truth, which is that the whole trouble is that you never directly see the amplitudes. Okay, amplitudes, in fact, only ever relate to observation because we need them to calculate the probabilities of the outcomes that we do see. Okay, but if I look at n qubits, I don't see this list of 2 to the n amplitudes. I just see n bits. Okay, I force nature to make a decision about which outcome it gives me. Each outcome x occurs with probability absolute value of alpha x squared. And then that's it. Okay, so yes, I could make an equal superposition over all the answers to my computational problem, even if there are exponentially many of them. That's even an easy thing to do with a quantum computer. Okay, but if I do that and then I measure, then the rules are very clear that all I'm going to see will be a random answer. Okay, and if I just wanted a random answer, I should have just flipped a coin a bunch of times. I could have saved all the billions of dollars to build the quantum computer. Okay, so the only hope of getting a speed up from a quantum computer is to exploit the way that the amplitudes, being complex numbers or having minus signs, work differently from probabilities. Okay, with every quantum algorithm, the basic goal is to choreograph a pattern of interference so that for each wrong answer, some contributions to its amplitude are positive and others are negative, so they're canceling each other out. Whereas for the right answer, the one I want the different contributions to its amplitude to be pointing in the same direction, so they add up. Okay? The tricky part is that I've got to do that even though I myself don't know in advance which answer is the right one, if I already knew what would be the point, right? And I've got to do this faster than the fastest classical algorithm. Okay? So this is like a really bizarre hammer that nature has handed us that we can then look for, are there any nails that can hit, right? But like the universe has not, we are not entitled to, that the universe will deliver anything that this is good for, okay? We should be grateful for what we have, is what I'm saying. Okay, so what are the main known applications of quantum computers? Okay, so I've got a little slide where I would put them into 3 categories. Okay, so the most famous application of quantum computing, right, the thing that really put it on the map for the wider world when it was discovered 30 years ago, was that it so happens that there are fast quantum algorithms for factoring enormous composite numbers into their prime factors, and for solving a few closely related problems in number theory and group theory, okay, like discrete logarithms, problems involving elliptic curves. Okay, this was the breakthrough of this guy, Peter Shor, and this is what made like these kinds of people interested in quantum computing, like intelligence agencies. Okay, So anytime we visit a website, we're using HTTPS, or we send a signal chat, we send our credit card number, right? Our data is being encrypted with cryptographic codes that depend on the belief that these specific problems in number theory are hard. Okay? What Shor's algorithm shows is that if and when someone builds a scalable quantum computer, then that is no longer the case. This has motivated a push, which is already underway, to try to migrate our whole security infrastructure to what is called post-quantum or quantum-resistant cryptography. Okay, we do have some good candidates for post-quantum crypto systems, for example, based on lattice problems. Okay, and NIST and other government agencies and companies such as Google have already been trying to start this migration. Even if you thought that scalable quantum computers were only coming, say, 10 years from now, I think that the time to start migrating would be now. Okay, for example, there are apparently about $200 billion worth of early Bitcoins, okay, including Satoshi's original Bitcoins, okay, whoever, whatever Satoshi was, okay, that are sitting around in wallets that are only protected by elliptic curve cryptography that a quantum computer will presumably be able to break. Okay, so, it would be easier to solve that problem if someone were in charge of Bitcoin and were able to make the decision to migrate this. But by design, no one is in charge of it. Okay, so that's going to be an issue. Okay, so now, this is this application of quantum computing, while it is of great, let's say, geopolitical and cybercrime interest, is hard to put forward as a positive for humanity. It is a giant headache, that if we deal with it, then hopefully we'll all just be back where we started. Okay, so that brings us to the second application, which was Feynman's original one, and which I think is still the economically most important one that we know. Okay, which is that a quantum computer would just be a general programmable device for efficiently simulating pretty much any quantum system of interest to you. So this could be useful for people studying high-temperature superconductivity or photovoltaics, batteries, the chemical reactions that are used to make fertilizer, a bunch of things like that. And in my view, this is sort of our best shot at doing something economically valuable with a quantum computer, certainly in the near term. Okay, and so I hope that will work out. Okay, but this is this is still it's a more limited class of applications than many people would like, and that brings us to the third category, which is everything else. Okay, and so. When you read, let's say, what the quantum computing startups are saying, especially the ones that are now having IPOs and getting valued at $20 billion or whatever, or what people are saying in the business world, right? It's all about quantum computing is going to revolutionize machine learning and optimization, and pretty much every and AI and finance and pretty much every practical thing that we do with our computers. Okay, and here I think the case, at least based on the quantum algorithms, that we know is much iffier. Okay, we do know some quantum algorithms that could give some advantages for these kinds of tasks. Especially there is one called Grover's algorithm, the second most important quantum algorithm after Shor's, and this has a much broader range of application. Grover's algorithm can be used to search any list of n possible solutions using a number of steps that only grows like the square root of n. Okay, where classical brute force search would need order n steps. Okay, so that's like you look at a CS textbook and just about anything, any algorithm in it has some for loop where you're checking a bunch of possible entries in a database or a bunch of possible solutions to a problem. Just about any algorithm that you can think of has some step that can be Groverized. Okay, the disadvantage is that this is not an exponential speed up, right? It is merely a square root speed up from n to square root of n. You might say, well, that sounds pretty good, right? I'll take it, right? And indeed, that could eventually be relevant, but probably not for a while. Okay, the issue is to build a quantum computer at all that could run Shor's or Grover's algorithms, you're going to need something called quantum error correction. Okay, we have just within the last year or two started to see quantum error correction actually work for like protecting 1 qubit, more or less, okay? So it is starting to work like the theory says, but it's going to incur an immense overhead. Optimistically, maybe an overhead by a factor of 1 million. Let's say, okay, so now the question is not comparing n to square root of n. The question is comparing n to 1 million times square root of n, right? And and eventually 1 million times square root of n is indeed less than n, but that only happens once n is in the trillions. Okay, so that's kind of the issue with these Grover speedups. And when you go outside of that, we've been trying for decades to find quantum algorithms for optimization and machine learning problems that get more than the Grover speedup. But that's been very challenging. To make a very long story short, most of the speedups that we know, are either for very, very specialized problems, or they're modest, or they are kind of speculative. Like we don't know if the speedups are actually real. Sometimes a quantum speedup will stand for a while, and then it will be destroyed by someone finding a better classical algorithm for the same problem. Okay, Yiwen Tang, who was a grad student in this department, now faculty at Princeton, back when she was an undergrad working with me, had one of the biggest breakthroughs on dequantizing a quantum machine learning algorithm. Okay, so that that's part of the challenge here. You have to survive Yiwen. Okay. Okay. But now I like to say, for me personally, the zeroth application, the one that I care about more than any of these, is just disproving the people who said that quantum computing is impossible, right? If we can just do that, then I think it's worth all the investment, okay? And anything useful that you can do, that's just icing on the cake, okay? This is not the case that people make to the funding agencies, but again, okay, so here's like a little picture of in computer science we like to organize things into these classes and call them by different capital letters. Okay, and so we have P, which is like the problems that are solvable in polynomial time by a classical computer, and then NP, which is all the problems where a classical computer can at least efficiently verify the answer. Okay, and then at the top of NP are these famous NP complete problems. Okay, and of course our most famous unsolved problem is whether P equals NP. Okay, but in the meantime, we also have this quantum generalization of P, which is called BQP, bounded error quantum polynomial time. And I drew it with this wavy border because everything quantum is spooky and weird. Okay, but BQP contains at least a few NP problems that are not known to be in P. Okay, that was Shor's breakthrough, but we don't think that BQP contains the NP complete problems. At least if it did, that would be a revolution, almost as great as the discovery that P equaled NP. Okay, in the other direction, we don't know whether BQP is contained in NP. There might be problems that a quantum computer can solve where a classical computer can't even check the answer. Okay, simulating quantum systems might be an example of such a problem. Okay, so where are we now with this? Maybe the best known thing that I've contributed to quantum computing theory in, I guess, 27 years of working on it was, a lot of the theory that led to what we now call quantum supremacy experiments. I didn't coin that name, by the way. If you don't like it, you can blame John Preskill. Okay, but these are experiments that have been done actually by several different entities. Some of the first ones were done by Google. And just a year ago, they were able to build a chip with 103 superconducting qubits, and they were able to use this chip to get some mathematical information that we do not know how to get classically from the largest existing classical supercomputers in less than about 10 to the 25 years. Okay? Now, what is the information that we got? All right, well, I hope you're sitting down. It is these strings of 103 bits are statistically unlikely to have, to have not been the outputs of this quantum circuit. Okay, so I didn't say that it was going to be very interesting information. Okay, in fact, even to verify that the quantum computer did what it's supposed to do, in this case, would also take 10 to 25 years, as far as we know. Now, just within the last year, this has been improved upon by both Quantinuum using its trapped ion devices and Google. Actually, Dave Bacon is right here. I think has been involved in some of this work. But they're now starting to do actual simulations of physical systems, such as the Fermi-Hubbard model in Quantinuum's case, or what's called circuits of out-of-time order correlators, OTOC circuits, okay, where you're actually just computing one specific number. Okay? Instead of just sampling these weird distributions, right? You're computing this number faster than anyone knows how to compute it classically, and you can verify that the quantum computer is doing the correct thing, if nothing else, by comparing its output to second quantum computers, okay? Or comparing it to an actual physics experiment. Okay, we still don't have devices at the scale where they could run Shor's factoring algorithm. Let's say that probably needs our correction. Okay, so now I can get back to the philosophy part. Okay, so there's been this sort of question, since the earliest days of quantum computing, of sort of what does this mean about the nature of the world? There is. Famously, this what's called the many worlds interpretation of quantum mechanics, which goes back to this guy, Everett, who was a grad student when he published this, but then Niels Bohr hated it, so Wheeler, his advisor, told him that he had to censor what do you mean, and then he got disgusted by that, so he left physics and became a nuclear weapon strategist instead. Okay. But okay, what does the many worlds interpretation say? It says, the key thing it says is just that this giant list of amplitudes is the most fundamental ontological reality that there is. Okay, so in particular, like the whole reason why people have argued about the meaning of quantum mechanics for 100 years is that, like I said, when you look, when you measure, right, then you see the outcome x with probability absolute value of alpha sub x squared. And you might say, well, what the hell do you mean when you look? Right? The laws of physics are not supposed to have clauses like when you look. Right? They're not supposed to talk about observers or consciousness or measuring devices at all, right? We're supposed to be made of atoms also, which are obeying the same laws as everything else, okay? And so many worlds, just says, yeah, absolutely. We agree with that, okay? Everything obeys the same laws. The laws are those of amplitudes. Okay, they're those of linear evolution of the vector of amplitudes, and what we call measurement, what we think of as measuring a qubit, is actually just you becoming entangled with that qubit. Okay, so like a measurement you should think of as just an ordinary linear transformation, unitary transformation of a quantum state that now will also involve all the atoms of you. Of your body, your brain, or whatever. So here is you considered as a quantum state. Here's the qubit that you're measuring. Okay, and all that happens in a measurement is that the two become entangled. Okay, so which means that now there is, with amplitude alpha, the qubit is in the state 0, and also you, like your brain, maybe also, the air and the radiation in the room surrounding you have recorded the fact that that qubit is 0. And then with beta amplitude, the qubit is 1, and you and your measuring device and the room and so forth have recorded that the qubit is 1. Okay, and then, so this is a branching event, and then a whole bunch of branching events continue with nothing to ever stop them. Okay, and the many worlders would say, and all of these outcomes just stay there forever, because that is what the math says, right? So in particular, you should have, quadrillions of doppelgangers, whose lives turned out differently from yours, and they are all equally real, right? Now, what can be hard to convey to people, there's a lot that you could say, they're for or against this, but there's a sense in which this is just the conservative option, right? Okay, or anything else is sort of radical. Okay, so what are the main? I think the main alternatives to this are there is either what's called Bohmian mechanics, Bohm de Broglie, which basically accepts that there is this giant wave function. Okay, this giant vector of amplitudes, but then it says, okay, but in most of the branches, nobody is home. They're just kind of ghost towns. Okay, and then there is one branch that is the real one, that is illuminated by the light of consciousness. Namely the one we're in. Okay, and and all the the other branches are just there because the math needs them to sort of push around the true branch in a way that exactly matches the predictions of standard quantum mechanics. So there's no way to test it. Okay, so that's okay. So that's a possibility. Second possibility is what I'll call new physics. So it could be that once you get up to the scale of you, or let's say a cat in a box that could either be alive or dead or whatever, then some as yet unknown physics takes over, and superpositions at that scale are simply unstable. They just dynamically collapse themselves into one state or the other. That actually makes an empirical prediction that in principle could be tested. So far, we have seen no sign of that. Okay, but of course, if building a quantum computer were to lead to the discovery of new physics, I think that would be more exciting than a mere success in building a quantum computer. I would love for quantum computing to fail in that way, right? For it to succeed would be like a disappointment by comparison. Yeah.
But it doesn't take new physics. It just takes a phase transition when you go to the macroscopic.
Well, I would say that if the Schrodinger equation is universally true, then it may appear to us like there is this phase transition happening, but the true laws of physics would be saying all the other branches are still there. They have not disappeared. Right? If you want them to disappear, then you need some physical mechanism that will make that happen. Right? That's what. Okay, that's what I'm saying. These. I'm not telling you which option is the right one. I'm just telling you that these are the options. Okay, and then the actually original view of the fathers of quantum mechanics, Bohr and Heisenberg and so forth, was like a very, very sophisticated version of just shut up and stop asking this question. Okay, all right. I like to say it was shut up and calculate, but except without shutting up about it. Okay, so maybe these are just bad questions. Okay, but now I want to come to a famous challenge that was issued in 1997 by David Deutsch, who was a co-founder of quantum computing, and he said, to those who still cling to a single universe worldview, I issue this challenge: explain how Shor's algorithm works. I don't merely mean predict that it will work, which is merely a matter of solving a few uncontroversial equations. Deutsch was never a detail guy. Okay, I mean provide an explanation. When Shor's algorithm is factored a number using 10 to the 500 times the resources that can be seen to be present, where was the number factored? If the visible universe were the extent of physical reality would not remotely contain the resources needed to factor such a large number. Who did factor it then? How and where was the computation performed? Okay, so what can we say about this sort of provocative argument? So first of all, Deutsch is not saying that if you build a quantum computer, then this is an experimental test of the many worlds interpretation, right? He's not saying anything nearly that simple, okay? And why not? Well, because just, everyone who agrees with quantum mechanics, regardless of their interpretation, they all agree that Shor's algorithm will work, right? As he said. Right? For it not to work, something has to be wrong empirically with our understanding of quantum mechanics. Okay, now Deutsch, in fact, has said that in his view, the double slit experiment, from the 1909, already proves the many worlds interpretation. Right? It's already, absurd to speak about it in any other way. But then he adds that for many people who are too psychologically weak to see that, it will be helpful to them to be hit over the head by seeing a quantum computer, factor a 10,000 digit number. Okay, so now I would say the philosophical problem is there any sense in which scalable quantum computing, either the idea today or hopefully the demonstrated reality tomorrow, adds to the case for many worlds? So my view is that at the core of Everett's picture is the exponentiality of the amplitude vector. And yes, quantum computing is unique in how it makes that aspect of quantum mechanics impossible to wave away. But if you ask the more metaphysical question, like is anybody home in the other branches, then quantum computing is completely silent about that, right? So, and in fact, there's even a further thing we can say, which is that ironically, to whatever extent a quantum computation works, such as Shor's algorithm, right? It worked because we got all these branches to interfere with each other constructively and destructively, and that means that they sort of never fully got to establish their identities as separate universes at all, right? They were just one giant interfering quantum mechanical blob. Right? And to whatever extent they really branched off as universes, then to that extent we only got to see one of them. Okay? So there is something funny about making a case for many worlds on this basis. All right, so the rest of this is faster. But I wanted to say a little bit about the complexity theoretic Occam's razor. So should there be an inductive bias against physical theories that predict computational superpowers? So you might wonder, how could changes to the laws of physics yield computational superpowers at all, right? So in order to answer that, I would like to present to you the Zeno's finite time Goldbach decider. Okay, so Goldbach's conjecture is says that every even number 4 or greater can be written as a sum of 2 prime numbers. Okay, this is one of the most famous unsolved problems of elementary number theory. Right, it has been checked all the way up to the quadrillions, but of course the trouble is that there's still infinity cases left. Okay. So, but, suppose that we could just have a computer that we could just speed up arbitrarily. Okay, then an idea would suggest itself. Why don't we just test the first case of Goldbach in 1 second, and then test the second case in half a second, test the third case in 1/4 of a second. Okay, and then the next one in 1/8 of a second, and so on, so that after 2 seconds we would have tried all infinity of the cases, right? Like, why doesn't anyone try that? Okay, well, there sort of are people who do. There are people who overclock their microprocessor. Okay, but some of you might know the issue. If you overclock your processor too much, it will melt. Okay, that's why all these data centers that are being built have all this cooling in them. Okay, but cooling costs energy. In fact, computation itself, the way we normally do it, costs energy. Okay, and you might wonder, what is the ultimate limit here? Okay, as far as we can say, based on known physics, the ultimate limit seems to occur somewhere around 1 Planck time, which is 10 to the minus 43 seconds Okay? And what happens is that if you try to run your computer faster than that, like faster than 10 to the 43 operations per second, then like whatever comprises your computer is using so much energy to cycle through states that it exceeds its own Schwarzschild radius. Okay, what does that mean? It means your computer collapses to a black hole. Okay, which I've always liked as nature's way of telling you not to do something. Okay, another idea is what we could call relativity computing. Okay, and this is where you just start your computer working on some hard problem, you leave it on Earth, then you board a spaceship that accelerates to nearly the speed of light, you decelerate, you return to Earth. Now in Earth's reference frame, billions of years have passed, civilization has collapsed, if it didn't, in like 2028 or so, but by then surely it has. All your friends are long dead. Okay, but if you can find your computer in the rubble and it's still somehow had a power source, then you can get the answer to your hard problem, right? And so then the question is, well, why doesn't anyone try that, right? And I think actually the issue here, again, it's about energy. Okay, it's about how much energy would it take to accelerate to so close to the speed of light that you would get this exponential speed up, and you can calculate that again you would need an exponential amount of energy. Okay, and so again we're just trading one exponential for another one. There is an old idea that you could use time travel, closed time-like curves, to solve hard computational problems. It's not as simple as, just, if I could go back in time, I could just reuse the same time over and over, because that doesn't take seriously the grandfather paradox, right? Like, what if you go back in time and you kill your grandfather, right? And so then, nature has to find some consistent solution. Okay, so David Deutsch, the same one from quantum computing, had a famous paper about closed time-like curves, where he said, look, again, quantum mechanics comes to the rescue here, because it allows for solutions where, let's say, if you go back in time and you kill your grandfather, what that really means is that you were just in a quantum state. Okay, where like with half probability, you go back in time, you kill your grandfather. With half probability, you never existed. And so what does that mean? It means you were born with half probability. Everything is consistent. There's no paradox. Right? Okay, and you can prove that at least in a finite dimensional space, at least one such fixed point will always exist. But then you get a new problem, which is how hard would nature have to work to find that fixed point? And in finding that fixed point, it turns out that nature could again be forced to solve a hard computational problem. Okay, you could basically make it so, like the usual story is, imagine that you go back in time and you tell Shakespeare what plays he's going to write. And he's like, man, thank you for saving me a lot of time. And he just copies down what you told him, and then those plays come to you. And so unlike with the grandfather paradox, here there is no contradiction. Everything is consistent. Okay, the only problem is that somehow Hamlet and Macbeth appeared without anyone ever writing them. Okay, so you could use that same kind of idea to force nature to solve an NP-complete problem with only polynomial resources. Okay, in fact, you can even do more than that. So John Watrous and I had a paper in 2009 where we said you could solve all the problems in the class P space this way. Okay, and that's exactly the right answer. Okay, do everything that a classical computer can do with polynomial memory. And then we had a later paper where we said if the size of what goes through the closed time-like curve is unbounded, then you can actually solve the halting problem. This way, you can literally do things that are Turing uncomputable. Okay, but now the question is, should we just treat these results as just additional arguments for why, probably closed time-like curves don't exist in reality, right? So this is the question of Occam's razor with complexity aftershave. Should we penalize physical hypotheses, not only for high descriptive complexity, but high computational complexity? My own view is that we can't be too dogmatic about this. Because if we were, we would rule out quantum computing also, right? As in fact, many of the quantum computing skeptics do. They say quantum computing cannot work Why can't it work? Well, because if it did work, then factoring would be solvable in polynomial time, right? An obvious absurdity, right? But, okay, this position, some of them are still going at it. But, as the experiments proceed, they're going, they seem to be getting boxed into a tighter and tighter corner here, right? So like I might want to have some bias against, nature being able to solve NP-complete problems with polynomial resources, let's say, but not an infinite bias, right? The fact that quantum computing merely seems to expand P by a little bit, let us solve factoring, but not NP-complete problems, to me is a reason to regard it as more plausible. But on the other hand, like no fast solution to NP-complete problems feels not that dissimilar to, let's say, no superluminal signaling or no perpetual motion machines. Tellingly, the same physical hypotheses, like closed time-like curves or like nonlinear modifications of quantum mechanics, tend to violate all three of these principles. So there seems to be some kind of connection there. And that actually brings me to the last thing I'll tell you about. I'm going to skip over the whole thing about the black hole information problem because I don't have time, and we don't, have a black hole to slow down time with. Okay, but I can tantalize you with these slides. Here's Alice jumping into a black hole with a firewall, and here's this this whole story that Daniel Harlow and Patrick Hayden came up with 13 years ago for like trying to explain what is going on in this particular paradox about black holes by saying, it would just take too long. It would take too long of a computation to do the experiment that would cause quantum field theory and general relativity to break down as it was predicted that they would. Okay, and so in some sense, our physical theories are protected in the vicinity of a black hole by certain problems not being solvable in the mere 10 to the 67 years that let's say, a black hole with the mass of our sun would take to evaporate, but rather needing 2 to the 10 to the 67 years to solve. Okay, so it's a very, very neat argument. If people want to ask me about it later, they can. Okay, but now just within the last few months, actually, when I visited the Santa Fe Institute, I worked with Gulcha Cardis and Harrison Hartle on a much more prosaic sort of example of computational complexity as a form of armor. Protecting our effective theories in physics. And this has to do with just the second law of thermodynamics. So just gas particles in a box. Okay, and so what we did is we constructed a toy situation where if P were equal to NP, so if, in fact, if there were no one-way functions, so like if there were basically no cryptography based on hard problems, then you could appear to reverse the second law of thermodynamics by building a box that collects all the gas in a box onto one side of it. Okay, so so Maxwell's demon is the famous paradox in physics where, you have like gas in a box and then there's a demon that just by opening and closing a door strategically is able to move all the gas to one side of the box, which seems to decrease the total entropy of the universe in violation of the second law. Okay, and there's a classic resolution of this paradox due to I guess Landauer, Bennett, and others that says, okay, this is not actually violating the second law. Okay, and why isn't it? Well, because the entropy is still there, hasn't gone away. Where it's gone into is the demon's memory. Okay, the demon has to remember information. Information does not get deleted from the universe. It just gets transferred into the memory of the demon's computer. Okay, now what we can show is a situation where if P were equal to NP, then we can uncompute the demon's memory. Okay, so we can start with like a simple initial condition, and if we have deterministic reversible classical dynamics, then entropy appears to go up, but that entropy is really just pseudo-entropy, right? And by using the fact that P equals NP, we can unmask this pseudo-entropy. Meaning, like, first the daemon collects all the particles on one side, then the daemon uncomputes, or just massively, massively compresses what is in his memory. Okay? And then we appear to reverse the second law. I should caution you that in practice, either chaos or quantum mechanics will probably make our strategy fail in most realistic physical systems. Okay? But even so, we've shown that the appearance of the second law can be protected only by computational complexity, just like general relativity and quantum field theory are in the vicinity of a black hole in the Harlow-Hayden scenario. Okay, and this was a little picture of our system. We did a little simulation of it. Okay, yeah. All right, so concluding thoughts. More than a century ago, knowledge and information, despite their apparent anthropocentrism, snuck into our best explanations in physics, for example, via statistical thermodynamics of Boltzmann and via the no signaling principle in relativity. Okay? So should we be that surprised if computational limits would likewise sneak into physics explanations in our own time? Now, one difference is that progress in pure math, like a solution to the P versus NP problem, would help clarify which of the computational limits are real. So, there are unsolved mathematical questions here. Okay, but I think, part of the story is a lot like the earlier story of thermodynamics here. And if you want to know more about this, you might enjoy my survey article from 2011, even though a lot of what I talked about was actually newer than that. But thank you for listening.
I think maybe 2 questions.
Yeah, sure. Yeah, we had some questions during the talk.
Pick whomever.
Yeah. Okay.
So one thing I've always wondered
Yeah.
is why does it seem so hard to come up with useful algorithms that use quantum computers?
Yeah.
Does that say something like fundamental about the actual complexity, difficulty of that problem? Or is it just that we haven't tried hard?
Yeah. I mean, the way that I think about it is that, like I said, nature handed us this absolutely bizarre hammer that didn't have to be useful for anything, right? We're lucky that, there are any purely classical problems that happen to map on to this interference phenomenon such that, you can choreograph the interference to get a speed up. I think like after Shor's algorithm, you got like a sort of Rumpelstiltskin phenomenon. Right, the fable of Rumpelstiltskin, where like if you could like spin some straw into gold, well then then spin this 1,000 times more straw into gold, right? Like okay, if you can do factoring, then there must be this vastly more that you can do, right? But part of the issue is that if you just look at the landscape of computational problems, right? Like we have this huge number of problems that are already in P. Right, where you could only hope for a polynomial speedup from a quantum computer. Then we have this huge number of problems that are NP complete or harder, right? And we said, we generally don't believe that quantum computers will be able to solve NP complete problems, right? So if we take that off the table, then what we're left with is the no man's land in between P and NP complete, right? And what is there? Well, it's much sparser there. Okay, we've got factoring, we've got discrete log. For those things, we have quantum algorithms. Okay, we've got some other stuff like lattice problems where we don't yet have quantum algorithms, and maybe we should hope that we won't, because if we did, then like all our public key cryptography is gone. Right? We should hope that some of that stuff stays hard. Okay, we've got graph isomorphism that some people, including people here, have worked on. We've got a few other things, but I think if anyone who really wants more quantum algorithms, the first thing that they ought to be doing is expanding the space of problems to look at, okay? And that might be like weird things that people haven't thought about so much. Okay, I had a proposal 7 years ago that you can use quantum computers to generate cryptographically certified random numbers, which you could then use for proof of stake cryptocurrencies, for example, right? So that's weird, right? That's not, that's like not even a computational problem, like in the usual sense of P and NP. But if anyone really cared enough, then they could actually do this today, right? And with current hardware, it's been demonstrated experimentally, right? And so I think we ought to be looking for more really weird stuff, right? Sometimes like when the fruit is too high on the tree because all the low-hanging fruit has been picked, then the solution is to find some other orchard. So that would be my best suggestion. Yeah.
What about the stuff outside of NP?
Yeah, sure. I mean, we can look there. I mean, quantum simulation is there, right? But then, it becomes a little bit sometimes less natural to write those problems down because we don't even have an efficient criterion for checking the answer. Right? Yeah.
So there's a more basic reason why physicists have to take computational complexity into account, which is the predictions of a theory must be computable in order to be tested. And in fact, they mostly aren't, so you could actually say that what's been tested so far is not the theories, but tailored approximations of them.
Yeah. Well, so look, the way that physicists deal with this in practice is that they say, look, we don't have to test all the predictions of our theories, right? It is enough to find some predictions of our theories that are novel, that go beyond, what the previous theory said, and that we can compute, and that where we can do the experiment and we can compare the two. Right? And if we see agreement there, then provisionally we will accept that theory, right? This is what has been done for hundreds of years, right? Where we don't test quantum field theory on the scale of a person, with all its Avogadro's number of particles, but we do test it on the scale of a few particles, and we see that it works completely reliably, and then we sort of create these explanations where, just like with software, where we have a separation of abstraction layers, and like each abstraction layer, we can sort of explain it by reference to the one below it. So we have these things that we call chemistry, we call biology, where each one tries to give a higher abstraction layer on the basis of the ones below it. So that would be my... Well, quantum computing changes the underlying model of computation that nature would be using at the very lowest level. Yes, that is why it is interesting.
So let's thank Scott Aaronson.